Thank you everyone. Today I will talk about our paper Learning Trajectory-Aware Transformer for Video Super Resolution. Video Super Resolution aims to recover a high-resolution video from a low-resolution counterpart, and the main challenge is how to exploit temporal information of whole video by aggregating misaligned video frames. So if detailed textures can be discovered at distance frame, video qualities can be greatly enhanced. In this paper, we propose a novel trajectory-aware transformer to model the long-range information, where we define the video frames into pre-aligned visual tokens along trajectories. This is the framework of our method. Each trajectory in our approach can be formulated as a sequence of token coordinates over time. The tokens in our approach are formulated from video frames. The output SR frames result can be expressed by trajectory-aware attention A and the reconstruction network R and upsample U. In the component trajectory-aware attention, we use a hard attention to transfer the most similar K from other LR frame, and a soft attention to fuse the transferred token into current LR frame, where the most similar token will be enhanced, while less relevant ones will be relieved. The use of texture from a large scale often helps to recover more detailed texture, so we propose the cross-scale feature tokenization to obtain the extractor features from a large scale while keeping the same size as output tokens. We propose a location map for trajectory generation. It can be represented as a group of matrices over time. The relationship of location map and the tokens trajectories can be shown in the equation and figure. We update the location map over time to form the token trajectories, where O is the backward flow, S is spatial simple. By such a design, the trajectory generation can be expressed as some matrix operations, which are both efficient for computing and friendly for model implementation. Finally, we recap the formulation of trajectory-aware transformer and location maps. The equation indicates the index change of each tokens. For the experiments on the widely used RISE dataset, our method significantly outperforms other SOTA methods. On the Wemo training side, our method also achieves SOTA performance. Besides, for the hardware-independent metrics, it achieves higher performance while keeping the comparable prime and the flops. We also compare visual qualities of our and other methods. In ablation of trajectory-aware attention, trajectory generation can capture the relevant tokens. Trajectory-aware attention integrates tokens into current frame to produce clear textures. For cross-scale feature tokenization, the best scale of token used is 4, 6, and 8. For frame number during inference, the performance is positively correlated with the number of simple frames. We visualize the limitation of our method in this figure, and the trajectories are inaccurate when a rotation occurs. And the conclusion is we studied video super resolution by leveraging long-range frame dependencies and propose a trajectory-aware transformer in VSR. And we propose a novel location map to record trajectories, and the location map can online update efficiently by design. In the future, we will focus on evaluating our method in more low-level vision tasks and extending the trajectory-aware transformer to high-level vision tasks by more exploration. Thank you for listening.